So this is the core function, the core notebook, which controls the sensors and the camera for the input. So over here we are using the RPi GPIOs, Raspberry Pi GPIOs, and this is the core for the moisture sensor. Over here it takes in the moisture, um, whatever the data is from the moisture sensor, and then collects it over here. If the moisture sensor data crosses a certain threshold, and then it activates the pump. So if, let's say if moisture the moisture in the soil is below 80%, it activates the peristaltic pump to water the plants automatically. Also it takes in date time, and if the plant has been watered already, it doesn't do the same again and again. So that's one thing that prevents the plant from over watering over here. So this is the moisture data count. The threshold is set on the potentiometer on the moisture sensor module. Next, this is the humidity and temperature sensor, and they'll give the temperature reading as well as the humidity reading, and if they cross a certain threshold, it assigns a variable which is then taken in the Streamlit dashboard to project the data. Going ahead, this is the date time importing module, and for every 1 hour it takes in the temperature and humidity data to prevent excessive load in the web app. So for every 1 hour passed from 12 p.m. to 12 a.m. it continuously takes in data. So this is the data thing with the date time. Next, this is the Plotly Streamlit front end. Over here, syntaxes may vary because this is the Jupyter notebook and not the terminal. For the moisture sensor, we have taken over here dummy data because collecting a huge amount of data for 6 arrays and um, 6 plants in each array, so it goes off to 36 sensors. That's not possible. So over here it's taken as dummy data, but for the temperature, we have taken in the data for every 1 hour from the temperature sensor as well as for the humidity over here, and this data is being plotted as timely analysis for every hour. Going ahead, um, this is the average temperature count and average humidity count of the array. So it takes in all the data, divides it by 24, and then we get the average temperature count. And then um, the this temperature data is shown on the web page. If the average temperature is below 8, then the temperature is conducive. If it's above 8, temperature is still conducive, but if it goes above 20, it goes critically high. Same with the humidity and same with the moisture. If it's wet, the soil moisture levels are above 80, and if not wet, soil moisture levels below 80. That's already seen in the web page Streamlit. We can see that. And if we go to the YOLO model, over here I've trained the YOLO model till the 6th or the 7th function. Over here it's performing with the pre-trained weights, so we are just testing the pre-trained model. But going ahead, we are creating our own model. Over here we have taken in the zip files of the images and config files, and going ahead, this is the area where we train the thing. It takes about 6 hours to train the complete model, and once we have the model accurate, we can see the chart. And going ahead with that, we can also do a test for the thing. The output I've posted in the hackster.io page. After that, we need to convert the model to OpenVino to deploy that on the Raspberry Pi for inference. So this is the um, code for that. We go ahead, git clone a GitHub TensorFlow to YOLO v3 to TensorFlow directory, and then using a Python um, file, we go ahead and convert it to a .pb file from the .waits file, and after that it's converted to the intermediate representation once we get the YOLO v3 file. So that's all. That's saved in my file directory, um, the pb files and the intermediate representation. And after the environment for the YOLO for the OpenVino setup, we can deploy the .xml file on the Raspberry Pi. So over here it's performing the image function, the image model, the image framework, and then for every disease detected over here, it if, let's say if Alternaria or CDAR rust is detected, it assigns a variable called CDAR is equal to 0, and then the Streamlit frontend takes in that variable, and let's say if the CDAR or Alternaria variable is 0, then it shows that Alternaria is detected, and if there are fresh plants, it detects that fresh trees are there. So for every fresh plant detected, I assign a variable called fresh is equal to 0, like that. It measures and calculates and shows it up on the Streamlit dashboard. This is the backend which works, and further going, I'll the next video is on the Streamlit front end. So this was the sensor core notebook, and this is the notebook for setting up the environment for Raspberry Pi OpenVino and the USB stick. So first we need to download the latest version of the OpenVino from the OpenVino distribution. Once I have gone ahead and downloaded it in the downloads directory, then I create a file called opt-intel OpenVino and then extract the file over there. For the version you have downloaded, just check, just change the version over here. For me, it's the 2020.4.28 version, so I'm using that. And then I've created an environment with cmake, and this is for creating an environment permanently, so every time I don't need to create a new environment. And then um, this is for the USB stick. Once I've gone ahead and run this command, the USB stick is all set up, and then using the XML file that's created in the intermediate representation form, I can go ahead and run it in OpenVino. So wherever the file is located, choosing an image path, you can run the command and get the output. For me, the output is displayed on the hackster.io page, so you can view it over there. Thank you for viewing this. This is the backend of the whole system. The front end, Streamlit, and the Kepler is displayed using another video. Um, so this is all. Thank you.